All right, so let's get started. So last time we talked about depth first search and all the good, useful information we can get out of it. Distance that we'll do this semester. We also talked about pathfinding, even though you don't have to do it for your assignments. But this is more information that we can get out of our breadth first search run. And then we can use it for things like pathfinding for AI characters in games. So if we have this game where this is the player character, and say we have this AI character who needs to travel to this character. We want our AI to hunt down the player, and we want our AI to be, as smart as we can get them, at least reasonably. So our AI player, if we're not careful about how we code this, we just have some silly way to just go directly towards the player. That's how we want to code this. This AI character is going to go straight towards the player, get stuck in this little nook right here. Then our players say, hey, your game's buggy, fix your game, everything's broken, and this sucks. We don't want our AI players being that dumb and just getting stuck on the walls. So what we would like is for our AI players, our AI characters, to be able to move towards the player while avoiding these walls. Doing it from this alone, just the level data alone, can get pretty tricky to be able to do that. What we can do, now that we know breadth first search, though, is turn this level into a graph and then run breadth first search, which is essentially what you want to do in task 9. Create a graph and then run breadth first search on that graph. So instead of seeing this, we're going to build a graph for our AI characters, and our AI characters are going to see this. They're going to compute what node they're on. They're going to start at this node and say, this is my node in this graph. Find where the player is, and they're a little bit on the boundary, but I'd say they're on this tile right here. What tile is the player on? This one. That's this node right here. So the AI's job, instead of saying, okay, I need to hunt down the player, they transform it to, I need to find the shortest path from this node to this node. And when we build the graph, we're not going to create any nodes for our walls. Any wall doesn't get a node for it. So that's how we're representing our walls. And then any two tiles, any tile that we can traverse is going to be a node. And any two tiles that are connected, we're going to say our AIs can only move up, down, left, and right. We could add the diagonal edges too if we want more features out of this. But if you can get from one tile to another tile, we're going to add an edge between them. So any two connected tiles are going to be connected by an edge. And now the AI's job is to run breadth first search, choose their node that they're at as the starting node, and then run breadth first search either on the entire graph, or they could even shortcut it and stop when they get to the node for the player, and then work backwards to find the path from where they are to the player, which will be a shortest path. If there's ties, there can be multiple shortest paths, but it'll be a shortest path from the AI character to the player character that will avoid any walls. And then they can traverse that path. They can move down this path and get to that player character. And then they can constantly update their path as the player's moving around the game. Yeah. Oh. Yep. So when we built this game, it was running at 60 FPS, and they would run breadth first search every frame to constantly update their paths. So this algorithm works regardless of the configuration of the level. This level could be a huge, complex maze, and it doesn't matter. As long as there is a connection from the AI character to the player character, they're going to find that path and traverse that path. They're going to avoid all the walls. Breadth first search is going to go through every nook and cranny of that maze, even if there are dead ends and branching paths all over the place. It's powerful enough to figure all that stuff out. We can find all those solutions in that graph. We have actors in our task 9. We don't have to find the paths, but we still have to find distance. So we have actors, and we need to compute their degrees of separation between two of them, where their degrees of separation is exactly 1 if they're in a movie together, And if they're not in a movie together, it's the number of actors you'd have to traverse to be able to get to another actor. So if actor 1 was in a movie with someone who was in a movie with the other person, that would be 2 degrees of separation if they were never in a movie directly together. So same idea, we want to build a graph and run breadth first search. That's our idea. So we have our data, and we need to build a graph out of this data where 2 actors are connected by 1 degree of separation if they're in a movie together. Really sounds like an edge to me. So our nodes are our actors, and there's an edge between them if they're in a movie together. So if they're in a movie together, that's an edge. And if we build our graph this way, the degrees of separation is exactly the length of the shortest path connecting those 2 actors, which is their distance in the graph, which is exactly what we just learned how to find using breadth first search. It's going to be the number of edges, the minimum number of edges to get from one node to another node. It's exactly what their degrees of separation is. So your task for task 9, take this movie data, build a graph with all the edges, and then run breadth first search on, you get 2 actors, find their degrees of separation, run breadth first search with one of them as the starting node, and then find the distance to the other one. Using those 3 data structures that we talked about on Wednesday, you have 3 data structures, the queue, the set or array list if you're going to use an array list, and a hash map to be able to compute all the distances. Right. Any questions about task 9 before we go? The rest of today is the promised memory diagram, graph memory diagram. So any questions on task 9, task 8, task 7, task 6, or anything else? I'll take questions about damn near anything. But nobody's going to take me up on that offer. Anything before a memory diagram? And this is all the content for task 9 and the interview. That's it. The rest of today is prepping you for the quiz. Might as well get it up there. Is prepping you for the quiz through our very last memory diagram of the semester. Yay. I'm excited. And this is the memory diagram. I'll let you stare at the code while I'm waiting to see if anybody asks a question. This is our last memory diagram. I said this before, and I still believe it, is you could have done the graphs quiz last week before you even know what a graph is. You could do the memory diagram. There's nothing new here, but we are seeing new ways to combine things that we already know. So this memory diagram is a lot of review and also applying what we know in kind of a unique way. The big thing is having a hash map of values to an array list of values. Having the keys be array lists, or the values be array lists in a hash map is kind of new and interesting. But it's no new concepts. So most of this is prepping you, giving you just practice, something to study from, something to refresh your memory and all this stuff to better prepare you for next week's quiz. So, any questions? We got a question. Can you go over how to test the degrees of separation for task 9? Yeah, I'd be happy to. So you have the movies.csv data, which has all the titles in cast. And the idea is to do the same thing we did in task 7 and 8, where you're going to take that file and take just a few lines of the file, take a much smaller sample size from that, and then use that as your test case. So you create a new file with just a few movies. You can even trim down the cast list if you want to create just a couple movies with a few cast members, and then build your test case in a way that you can very easily verify the degrees of separation between 2 actors. So if you have 3 movies, the minimal test case would be 3 movies where 2 actors are not in a movie together at all. They're each in one of the 2 movies, and then the third movie has a common cast member that they were both in their movies with. So you have a degrees of separation of 2. It's like the simplest test case that really tests if you're doing the things you're supposed to. And if you want to get trickier with it, you can start creating graphs with a lot of cycles in them and some known degrees of separation to be able to build that test case. But it's following the same idea that we've seen. Create a smaller test case. Don't use the entire movies.csv because you really can't do that. Don't use the entire movies.csv because you're going to get in the situation where you're using your code to test your code. And as we've talked about a lot in this semester, that doesn't test anything. You're not testing anything when you do it that way. So smaller test files where you can easily verify degrees of separation is the idea. And I don't know if I don't really mention this in lecture. Maybe I should, but when you read the homework description, like I usually describe a test case or two in the description itself. Coding those as test cases can always speed up your testing process significantly. There were times where, if I can rant just a little bit, if I could, the Bayesian testing, Bayesian average, like I gave you the test case that gets rid of Bayesian comparator adds no ratings, adds no extra ratings. I gave you the test case for that right in the homework handout. The whole idea of the 4.99 average and the one rating of 5.0, that the 5.0 would be has the higher average rating, but not the higher Bayesian average rating. The intent was that you all code that test case. In the handout, I said like 10,000 ratings and an average of 4.99. You obviously don't have to do 10,000, but like 2 5s and a 4 would have sufficed to get rid of that incorrect solution. And that was a very common office hour question of how do I get rid of this incorrect solution? I don't know, code the test case I gave you. What are you doing? Like that was always my thought, but of course I was helpful in office hours. But yeah, coding up the test cases I gave you. So if you do want to use the whole movies.csv file, I gave you a test case where you know that the degrees of separation is 2. It's right there in the handout where I'm describing the data and saying the data is out of date, this actor's bacon number is actually 1, but in our data it's 2. That's a test case where you use the full data set. It's a good test case to see if your code's doing what it's supposed to be doing. And I went through and verified that one. They're never in a movie together, but there's lots of paths to get from Chris Pratt to Kevin Bacon in two steps. They've been in a lot of common actors together, but never in a movie together until the holiday special, which isn't in our data set. So it's a perfect degree of separation of 2 test case. All right, good question. I got a question. I'm happy. So let's go through this memory diagram. What we want to do is create a graph. This is going to be a graph of airports and adding 3 connecting flights between these 4 airports. So this will be a directed graph, unlike what we saw before where everything was bidirectional. In my other example, we had bidirectional edges, meaning whenever we added an edge, we added that edge to the adjacency list of both nodes to say that you can travel this edge in both directions. We're not going to do that here. We're going to add directional edges, meaning when we add an edge, we're adding an edge from Buffalo to Washington, D.C., but not vice versa. We're saying there's no flight from Washington, D.C. to Buffalo, but you can get from Buffalo to Washington, D.C. So a little bit different than the other one, but we want to talk about both types of graphs, or both types of edges, directional or bidirectional. And really, there's no such thing as a bidirectional edge. The way we represent our graphs, either an adjacency list or an adjacency matrix, bidirectional just means that you add 2 directional edges, one with the nodes reversed, one with the nodes forward and one with them reversed. So you add 2 directional edges, and we call that a bidirectional edge. But there's really only directional edges. It's the only thing that really exists. So we're going to create our graph, add these 3 edges, and then we have 2 paths, 2 potential paths in the graph. And we want to check if these are valid paths. So for each pair of nodes, we want a consecutive pair of nodes. We want to check if there is an edge in the graph connecting those nodes. So let's get on with it. So we're going to create our graph. I hope I don't have to go into the graph constructor. I'll talk about it a little bit, but I don't have to break it down in like 3 slides, right? So the constructor, we have new graph. We're going to call the graph constructor. It doesn't take any parameters, but we do get this, which is a reference to the object that's being created, but no extra parameters here. The method name, graph, the constructor, and then creating the graph on the heap, which is going to have one instance variable, adjacency list, and that adjacency list is going to be initialized to a brand new hash map. So we create a new hash map. The hash map constructor is internal to Java. We don't have the code for it in front of us, so we're not going to put it in our memory diagram. But we do still get, we're not going to put the stack frame in our memory diagram for the constructor call, but we still get the hash map object, and then that returns a reference, and adjacency list gets a reference to the hash map that was created, and we have this empty hash map on our heap. And we're going to call add edge, and we want to add an edge saying there's a flight from Buffalo to Washington, D.C. That's in plain English what we want to create. Let's go through how the code does this. And just like always for our memory diagrams, I'm going to turn off my brain a little bit and just go piece by piece through the code and just blindly go through what this code is telling me. What is this code saying to me? So graph, find graph in my stack. That's this reference. Dot means follow the reference. Graph dot add edge. So graph dot add edge. We're at this object when add edge is called. So this object is calling add edge, which everything's going to be through the graph class. It's the only code we have, so we know that this will be the case. But even if we didn't, this object is of type graph. So we're going to look in the graph class for an add edge method. We find it right here. So this is the method that's going to be called, and it's called through this object. So this is going to be a reference to the calling object, 350. So we put add edge, this is 350 onto the stack, and we call this add edge method with the parameters equal to the arguments. So from and to go on our stack, and they get assigned the values of our arguments, Buffalo and Washington, D.C. And then the first thing this method does is call this.addNode. So this.addNode, this is the calling object. It's of type graph. Look for addNode. It has a parameter A, so this is the calling object, reference to the calling object, and A is going to be the argument from, which is BUF. So intuitively, what addNode is going to do is initialize the node in the adjacency list. Get this node in the adjacency list if we haven't seen it before. So we want to do a check. Have we seen this node before or not? So to do that, this in add node, it's going to be the same reference, but in add node, this dot adjacency list dot put. So we're at this hash map right here, and we're going to call its put method. Again, internal to Java, so no stack frame in our memory diagram for put. A in our current stack frame is BUF, and then new array list. We're going to create a new array list for the value of this key value pair. So new array list, we're going to, whenever we see new, we're getting a new object on the heap. We get this array list initialized to an empty array list, and then that's what's added to our hash map. BUF to a reference to the new array list. And this is what I mean. This is all stuff we've seen before. I didn't say anything brand new that came out of nowhere for you, but I believe this is the first time we've had the values of a hash map being references to other objects on the heap. So we are still seeing a new way of combining things that we've seen before. So it is still new. It's still worth going through the memory diagram for, in my opinion at least, just to see these combination of ideas in action, but nothing brand new that we haven't seen before. So we've initialized Buffalo, the node, to a new array list. And we're going to do the same thing with Washington to Washington, D.C. So this dot add node to, this dot add node to WDC. So this calling object, the parameter A is equal to 2. 2 is WDC. And that's what we're going to put in this stack frame. Then we run the code. Oh, I didn't do the contains key. Well, good thing we get 6 of these. I get a chance to talk about it now. This dot adjacency list dot contains key. This dot adjacency list dot contains key. And this was at this point, dot contains key of A, which is going to be WDC. It does not contain the key WDC. So this expression is going to evaluate to false, but we're hitting it with the not here. So that's going to negate the Boolean. So we return false, but this is going to negate it to true. So our conditional for our if statement is going to be true, which means we are going to run the code inside the code block for the conditional. And that's, again, going to initialize this key value pair, WDC, to a new array list, get another array list on the heap, and map WDC to that array list, to a reference to that array list. Then we finally get to add the edge. So we're going to go to this dot adjacency list, this dot adjacency list dot get the from. So we're at the hash map for the adjacency list, and we're going to get the from, which is BUF. So dot get BUF, that resolves to the value stored at that key. So we have this reference. So this portion of the statement, this is how far we are, resolved to this reference OX480. We're going to hit that with a dot, meaning I don't care that this is a reference. I want to go to the object to which it refers. So after the dot, we're at this array list, and then we're going to call the add method and add to, in the stack frame is WDC, and add that to the array list. When we add to an array list, it's added to the end of it. We have an empty array list, so the next available index is 0. We're going to add WDC at index 0 in this array list. And repeat the process for the next edge. So add node. We're going to say add node from, well, we call our add edge. Add node of the from. We're going to get our add node on the stack. From is WDC. Now when we say this dot adjacency list dot contains key of A, which is WDC, that's true. So this resolves to true. We have a not here, so it resolves to false, which means we're skipping this code. We're not running the code block, and this method is effectively going to do nothing. This is exactly what we want. We don't want to reinitialize a node that we've already initialized. Because if we reinitialize a node that's been initialized, we're setting it to an equal array list. We're saying you don't have any outgoing edges at all. If we do that after we've already added edges, we're going to wipe out all those edges, and we're only ever going to have one edge per node in our adjacency list. Not quite what we want. So we're going to not initialize it if it's already been initialized. We skip over it. Don't do anything. For our 2, JFK, we haven't seen JFK yet, so we have to initialize it to a new array list. And we're ready to add the edge. We're going to do this. This is my one mistake in these slides that I know of anyway. This should be crossed out. This frame doesn't exist anymore. We're on this as the active frame. This dot adjacency list dot get the from WDC dot, so go to this array list, and then add the 2, which is JFK. So we're adding the 2 to this array list. Rinse and repeat for the third one. And the third one is our first time seeing Toronto, so we're going to initialize that to a new adjacency list. We've seen Buffalo before, so don't initialize it, and then add to Toronto's adjacency list the outgoing edge, saying there's a flight from Toronto to Buffalo. So that's the first half of what we want to do. We want to build a graph And then for your homework, you want to run breadth first search. For the memory diagram, we're just going to check a few paths to see if they're valid to do some computation with this graph. But this is how our graph is going to look in memory. We have our graph with one adjacency list, which is a hash map, where the keys are the nodes, and each node has a value, which is an array list of all of the nodes that can be reached from that node. If it's a bidirectional, if we have all bidirectional edges, I'll usually call them neighbors. These are all the neighbors of this node. Since it's directional, I'll change my terminology a little bit. These are all of the nodes that can be reached from this node. So from Buffalo, we can get to WDC, but nowhere else. So we can fly from Buffalo to Washington, D.C., nowhere else. From Washington, D.C., we can get to JFK, but nowhere else. From JFK, we can't go anywhere. From Toronto, we can go to Buffalo. So any questions on creating the graph or how it's represented in memory? We have 4 data structures in this example, 4 data structures to represent our one graph. Okay. No questions? Let's move on. All right, then we're going to create an array list for our first potential path. Path 1 equals new array list, arrays.asList. Technically, array list, there is a constructor call, a stack frame for this constructor call. There's a stack frame for the asList method. And both of these probably call a small multitude of other methods, a whole bunch of stack frames on the stack. We don't have the code in front of our face, so we're not going to trace it. That's our rule of thumb. We can't see the code, not going to trace it. So we're not tracing any of that code, but we still know, we do have to know what this line of code does. You have to be able to read what this does. It's going to create an array list, which you can all do at this point. We're going to create an array list on the heap with the values Buffalo, Washington, D.C., JFK, in that order. It's a sequential data structure, so the order does matter, and the order is preserved. And we get a reference to that array list on the stack stored in our variable path1. Then we're ready to check if this is a valid path in the graph. So this common misconception, I don't know if it is at this point in the semester or not, but just to reiterate it again, because I've seen this in the past. We have this print line call, and there's a temptation from some students to say, oh, print line's internal to Java. I can just skip this line. I don't have to do anything. I'm just going to write what is actually printed to the screen here, and I'm done. Which is, don't do that. Don't make that mistake. So print line, that is true. We're not going to put a stack frame on the stack for print line for exactly that reason. It's internal to Java. We're not going to trace it. But you still have to evaluate the argument. You still have to evaluate this, which we do have the code for, which is most certainly going on our memory diagram. And we got to trace out this valid path and do all the stuff that valid path does. That'll evaluate to a value, and then that value is just printed to the screen with no extra stuff on our memory diagram. But we still have to evaluate what's inside the parentheses because we have that code. This was trickier. Last time I mentioned this, it was even trickier. This isn't as isn't as hard to miss. Where it was trickier was when it was just like print line graph, for example. And graph had an overridden toString method, and you had to put that toString method call on the stack. You had to intuitively know, printing a value with an overridden toString, and I have the toString code. If the code is in front of your face, you have to trace it. So we're going to go into that toString method, put the toString on the stack, and then do all the memory diagram stuff with that toString method call. That was even trickier because it looked like it was just a call to print line, but knowing that print line would call the toString method, that was tricky. This one not as tricky, but still, don't forget, if it's inside a print line, you still have to trace it. It's still part of the trace. So valid, if you skip both of these, if this were a quiz, which would be a reasonable quiz question, I mean, it fits on a slide, it can fit on your quiz, if you trace this, but you didn't put either of these valid path calls on the stack, that's an easy, just no credit, try again. So don't forget to put those on the stack. And I hate seeing students lose credit because of things like that, especially if they know exactly what's going on in the course and all the concepts. But a silly mistake like that makes you go to the second chance quiz. I don't like to see it. I never like to see it. Just don't make that mistake, so we don't have to go through that. So we're going to put valid path on the stack. So graph.validPath, graph.validPath. This is the calling object, so this is going to be 350. Look in the graph class for a valid path method. It has a parameter named path, which is going to be equal to path1. And we're passing this by reference, which the easy rule of thumb here is if you have an assignment like between two variables on the stack, whatever's sitting next to the first one, that's what's sitting next to the other one. So path equals path1. Path1 has OX196 sitting next to it in our memory diagram. That means path is going to grab that value of whatever's next to it. Whatever's next to it, whatever the value is on the stack, that's what you're copying. Then path is going to get that OX196. Don't overthink it. Don't work too hard. Just whatever's sitting next to it, turn your brain off and just write whatever's next to this one is going to be next to this one. When it happens to be a reference, you just did pass by reference, or pass by value with the value being a reference, technically. So now path has a reference to this array list, and it can work with that array list by reference. We didn't copy the array list. You know this at this point, but I said I'd do some review. We didn't copy the array list. We don't have a second array list that we're working with, that are working copy inside the stack frame. No, we get a reference to it, and then we can go over to the heap and check out that array list. We could also modify it and mess up this array list if we're not careful. Or if that's what we want to do, then we can mess with that array list. We're going to enter the loop, and this is a lot of what I want to talk about in this memory diagram. We got to throw something new at you, right? Because I don't think, there's two things about this where I don't think we've ever shown this kind of structure, this kind of application in 116 at least. Maybe they did in 115. I kind of doubt it, but maybe. They might have. But let's take a look at what's going on here. So we're initializing I to 0. You've seen that 100 times. Inside this code block, we have I equals 0. We're going to check our conditional. And this conditional is a little different than what we've seen before. So usually we want to iterate over all of the indices of a data structure. To do that, we're either going to do I less than the data structure size, or I less than or equal to the data structure size minus 1. We're usually going to do one or the other. Here we're doing both. We're saying less than the size minus 1. So what we're not doing here is iterating over the indices of the data structure. I'll leave that conversation at that for now, but when we get to it, I'll explain more of why we're doing that. And then I, which is 0, check our conditional. Is it less than path.size minus 1? Path.size. I'm still, not often, but I'm still seeing this mistake kind of this late in 116. Y'all got to know this one. I would assume most of you, or probably all of you who show up to lecture probably do. But the size of the data structure is different than the maximum index number of that data structure. Some people are still saying the size of this data structure is 2 because that's the highest index value. That's completely false. The size of this thing is 3 because there's 3 things in it. In a memory diagram, it's easy to see that. I guess when you're coding, it's a little harder to think about that and reason about that. The size of this thing is 3. So array path.size is 3. Minus 1 is 2. So 0 less than 2 is definitely true. So we're going to execute the body of this loop because its conditional was true. We're going to check. We're going to call this rConnected. This dot rConnected. So this is a reference to the calling object, and graph.rConnected. From and to are our parameter names. And then from and to, figuring out what these are, get not really tricky, but we have to think about this a little bit. Path.getI, path.getI, I is 0, so BUF. Path.getI plus 1. Path.getI plus 1, which is 1, WDC. So our from and to, Buffalo and Washington, D.C. So this is the trick with, I want to talk about it now since I started the conversation, but this is the trick with the less than and minus 1, is we want to iterate over the edges of this path, which there are 2 edges in this path, but there are 3 nodes. There are 3 values in the array list, and we want to check each consecutive pair of values. So we have to be careful with our indices, because there are 2 big pitfalls we can fall in. One, we don't check all the edges. Here we would just check the first edge and miss the next one, or just in general miss the last one. And 2, we don't want an index out of bounds error. We don't want to go too far off of this thing. So we're iterating over our values. We're going to see is going to be 0 and 1, not 0, 1, and 2. And then we're going to access the value at I and the next value. So if we iterated over the values, all the indices of this data structure, and we didn't have that minus 1, when I is 2, we're going to access the value at index 3. We're going to get index out of bounds error. Everything's going to crash. It's not going to be any good. But if we're not careful and we don't check the last edge, what can happen, say we're just checking the first edge or just checking all but the last edge, what happens is you write your test, you check all the edges except the last one. Your test passes. You're just checking less things than all the things. And then you submit to Autolab, and Autolab says, hey, there's this incorrect solution called path is missing the last node, and your tests say that this is a correct solution because your tests aren't ever checking the last node. Then you pull your hair out trying to figure out what's going on. That's a tough error to find depending on how you're looking. It's a very tough error to find if you make that mistake. We call those off by 1 errors. Like if I had it'd be silly to make it in this way, but if this was a minus 2, for example, you'd have that issue. Maybe better if this were a 1, and this were I minus 1, and this was I. That would be a good setup to be able to make that mistake and really not be able to see that too easily. Be a tough one to spot. And this is why we give you so much practice with memory diagrams. We want to make sure you can read through code like that, because you could make a mistake like that, and foreshadowing, this is what all of next week's going to be about. You could make a mistake like that and not be able to see it immediately in your code, but if you go through a trace of your code, even if you don't draw out the entire trace, if you look through your code and think it through one line at a time and go through it the way Java's going to go through it, you'll be able to see those mistakes and be able to spot those. So we need to be able to read code, because you can look at this method and you can infer what it's supposed to do. That it's going to check all the edges in the path and make sure it's a valid path. Like you can all, before we go through any of the tracing of this code, you could all infer that that's what this code is supposed to be doing. Is it actually doing that is a tougher thing. For this, yeah, I'm not going to give you a broken memory diagram. But when it's your code you're writing for your homework, how do you look at your code and say, yes, this code does do what I intend for it to do? That's a tougher one. A lot of y'all submit to Autolab and let Autolab tell you. You got to be able to figure that out on your own by reading your code and seeing if it does in fact do what it's supposed to be doing. And then the next steps, of course, testing and debugging. But step 1, trying to eyeball it. Just look at your code and see if it's doing what it's supposed to be doing. And then go into the debugger. The debugger can really catch the things that you can't eyeball. So we're going to check the edge with this, which is another new thing that I know I've never talked about, and I'd be surprised if they talk about this in 250. Paul wrote this code, and I reviewed it. Neither of us even thought twice about this line. It's just kind of second nature to us. But this line does something pretty, kind of tricky. Not super tricky, but I want to explain this. Now is as good a time as any to talk about it. So let me first just go through what the line is doing, and then I'll talk about the kind of tricky thing. This .adjacency list .contains key. This .adjacency list .contains key from BUF. Does it contain the key? Yes, that's going to evaluate to true in this case. And then logical and, so true and evaluate this .adjacency list, this .adjacency list .get from. So get from is going to resolve to the value at that key. Dot contains to is WDC. Does this array list contain WDC? Yes, it does. True. We have true and true, so we're going to return true. So that's what the line does in this instance, in this case of what we're doing. And there's and we do two checks here, though. We check if the adjacency list contains a key, and then we access the array list at that key and ask it if it contains the 2. If we just had this line, this would be a dangerous line of code. If we just had this line without the first check, if we didn't check if the if the array list, the adjacency list contains this key yet, because if we say, hey, adjacency list dot get from, and somebody calls this method with a from that isn't in the adjacency list, we're going to get a key not found error and our program crashes. So if somebody calls this with a from that doesn't exist, they call this with LAX, and we don't have LAX in here, program would crash if we just had this line. But that line, this is all the same statement, so why wouldn't it crash anyway? If we're running that code and still running it and still accessing a value at a key that doesn't exist, why does this work this way? The answer is shortcut evaluations. So we have the logical and operator, which you should all be familiar with. I assume you're all familiar with. If not, it's going to return true if both operands are true and false otherwise. If either of them are false or both of them are false, it's going to return false. So if this is false, if the first operand is false, it doesn't matter what the second operand is. False and anything will always, always, always return false. So what Java does, and most programming languages do this, if not all of them, is going to shortcut the evaluation. As soon as it sees false and, it's not going to run the code that follows the and. So if our adjacency list does not contain from as a key, this code never executes. So this is an effective way to safeguard ourselves from a key not found error by taking advantage of the shortcut operation, the shortcut evaluation, by saying if this is ever being ran, from is in this adjacency list, because if it wasn't, this would have returned false, and we would have got shortcutted by the and. So we're doing our type checking and our accessing that value both in the same statement, and we can get away with that because of shortcut operations. Paul and I just use this so second nature that we didn't even think about it when we had this line in here. But I'm happy we missed it because it gives me a chance to talk about it here. Because I don't know where else you would see it for the first time. 116 sounds like a good place to see this for the first time. Assuming they're not talking about it in 115 at all, which I don't think they are, but maybe. The same is true with OR operations. If you have something or something, and the first operand is true or anything is going to be true. So it's going to be shortcutted, and the second operand would never be evaluated down to a Boolean. It would just be true. It would just return true without evaluating it. This is really important to know especially when the second operand has side effects, which in general just don't have a Boolean expression calling methods that have side effects. But if the second method has a side effect, you may or may not get that side effect depending on what the value of the first operand is. So it's important to be aware of that if you're writing some complex Boolean expressions in your code. But here, this whole thing returns true, that the key exists and the edge exists in our adjacency list. So that returns true, and then we're going to hit it with the not. So not true, that's going to be false. So we're not going to execute this code block. We're going to go to the next iteration of the loop. I is now 1. We're going to get the value at I, path.get1, path.get2, WDC, and JFK. Check if they're connected. WDC, this dot adjacency list dot contains WDC. We're good. This dot adjacency list dot get WDC dot contains JFK. We're good. It's there. So that both of these return true. So true and true returns true. Not true is false. And we move on to our our next iteration of the loop, which I should have a slide on it. And I do, if you want to give me -1 on this, I should update my I, cross out the 1, and put a 2 here. Technically, I does reach the value 2. And then when I reaches the value 2, we have 2 less than path.size. Path.size is 3 minus 1. 2 less than 2 is false, so we don't go through the loop again. And this is another pattern. This is the second thing. The first thing was messing with our indices to make sure we check exactly the 2 pairs of nodes or any consecutive pairs of nodes in the path. The second one is we're iterating over all the things we want to check, edges in this case, and checking if each edge does exist in the graph. And if it doesn't, if we have any issue, we're going to hit this return false and just return out of the entire method call, returning false. But if we've made it through this entire loop, if our loop is set up to check everything that we want to check, and we've never found something that was bad enough for us to return false, if we made it through all that, then we can infer that everything's good with this and we can safely return true because we've made it to the other side of the loop without ever returning false. So we can safely return true. This is a common pattern in programming that I don't think we've shown an example of yet in 1.16. Maybe we have, but I'm forgetting. But it's a common pattern. Check through everything. If we made it past the loop, we're good. So we're going to return true, print true, create another path to check, do the same thing. I 0, 0 less than 2 is good. We're going to check are connected, JFK and WDC, path.get 0, path.get 1. Contains key JFK. Go through our whole thing. Key is there. The array list is empty, so it's not going to contain anything. It certainly doesn't contain Washington, D.C., so this is going to return false. So we have not false, which is true. We do execute the code inside the conditional, which is going to return false. Whenever we hit a return statement, no matter how we got there, it's going to end the stack frame. The stack frame's over because we hit a return statement. It's going to shut everything down and return false. No, we don't go through the rest of the loop. We don't finish up the code of the stack frame.